started on the lecture. We're going to be doing IA today. I do that every time because I have muscle memory from 10 years of teaching it where I don't have these interchapter things. And they all show up at the bottom of my lecture slides. So I forget every time. Maybe in another couple of years, I'll remember to start on the IA. We'll see. Okay, so we're going to start on nomenclature. Okay, now we're going to be teaching the IUPAC nomenclature as our primary nomenclature. Now, this is the international standard for this. However, we will also have to teach you a little bit of common nomenclature, okay? Because a lot of chemical manufacturers and industry still use common nomenclature. IUPAC is not particularly popular with a lot of people. So, International Union of Pure and Applied Chemistry, this is IUPAC. This is the one people that provide a standard for naming inorganic and organic compounds. They do other things too, like units and various different things. But there are people that do not particularly like IUPAC. My advisor was one of them. He used to say, I was here first. They can go fuck themselves. I don't know. Complicated. No, I honestly do cuss them out in my head quite often. They make some really boneheaded, stupid decisions. They have also gone to a fight for like 7 years and didn't meet for 7 years. And finally, one of their members quit. I forget if he quit or died, but anyways, 3 of their members quit and ended up being gone, and then they met again. Yeah. And they made some really boneheaded decisions, like putting numbers in between letters so you can't pronounce it anymore. Yeah. So they do some really stupid stuff sometimes. They've also made it where some of their naming indicates rules, and people have gotten to the point where they think they're actual rules. And it's anyways, they cause chaos sometimes, but they're necessary. Because before them, it used to be where you'd go from like one university to another, and they could be down the street from each other, literally within a block. And they'd have different names for all the compounds, and you wouldn't know what the heck you're talking about. So,
why not just use their chemical name, like their composition?
Because then you have to have like this giant structure, and you'd have to check every single carbon, right? Yeah. So it gets, even with IUPAC, if you really want people to know what you're talking about, you still usually include the chemical, like 3-dimensional structure. Because even with IUPAC, it's so complicated in some spots and it doesn't really make sense in others that, yeah. Anyways, it's something. Okay, so given a molecular structure, you can always derive its IUPAC name piece by piece. Given IUPAC name, you can draw its structure piece by piece. It does accomplish this, and it does a pretty decent job for like normal things that you'd see in everyday life. So for majority of you, IUPAC will work great. Okay. Really, it's only where you start getting into more complex exoteric stuff that the rules start getting kind of weird and become a pain. Okay. Anyways, these are some different compounds that you can also represent with IUPAC names. These are actually their common names. Okay. And so here we have vanillin. This is vanilla, what you think of as the vanilla flavor taste and smell. Geraniol, also a flavor, taste, and smell. Azulene, see that beautiful color right there? Like an azure sky? That's azulene. Yeah. And that's what creates that beautiful blue color. Ooh, This is morphine. This is what most NSAIDs are based on. Pain relievers are based on the structure of morphine. Funny enough, there's actually kind of a debate whether anything after morphine and heroin was actually an improvement.
I don't think you can get better than morphine. Like when a person is dying, you don't say, "Oh yeah, give him some Tylenol."
You can. Heroin. No, heroin is actually more powerful. Significantly so.
Powerful, but not. I don't think you're powerful, but not like deadly. I think just like
Oh, it's not deadly. No. If properly administered in a medical setting, heroin is, and it was for 100 years, can be used just as well as any other pain reliever. The difference between them is that morphine isn't as powerful, and so it's harder to OD on it, and it's harder for people to really mess up their lives on it. And then when you get to the pain medicines, modern pain medicines are really just heroin put in a substrate that makes it harder for you to digest. And so it slows down the release. In fact, if you take modern pain medicines and grind them up, dissolve them, increase the concentration a little bit, you can inject them just like heroin. And they're just like heroin. Interestingly enough, you guys know how it's much harder to get pain medications now?
Yes.
Anybody experience that? Like,
go to a clinic, get a prescription, they count your bills every month.
oh, it's horrible, right? And it causes just chaos for people. Did you know that did not do anything at all? It has not decreased deaths at all because the pain prescriptions was not a major source of addictions when they put those laws into effect. Fentanyl had been on the rise for about 5 years before that, and it's fentanyl cases that they were seeing in the pain medication deaths. It was not the pain medications. They were actually on a 10-year decline before that. But nobody saw that data because fentanyl spiked it up so dang much. Yeah. Fentanyl has just been horrible. Fentanyl's awful. Fentanyl, very, very powerful pain medicine as well. Realistically, in a clinical setting, it's actually an entirely valid clinical and very cheap, very effective. The problem, of course, is always all of these things are addicting and physically addicting as well. Though there's a new treatment for addiction to pain medicines, actually, that completely takes away your ability to be addicted to them. But highly experimental, hasn't went through the trials yet, so we'll see. We'll see. Anyways, kind of a cool topic. Anybody looking for a topic for Colloquium, by the way, I would love to see a poster about that. It would be really neat. Yeah. You very well could. The history of heroin, the future of heroin. Actually, heroin's kind of coming back.
Is that a good thing?
No, in medical use. Yeah. For terminal patients, they're starting to look at using heroin because it's a lot cheaper. It's actually way more effective than morphine. So you have a lot better quality of life for those 3 months. The problem with heroin is that you develop resistance against it so fast. That's usually where problems start occurring. Exactly. Yeah, it's called Riding the Dragon. Yeah. Anyways. Oh, you can tell how many people have asked me about legal drugs first times. It's like every semester, probably about 20 or 30 people. So alkanes, these are going to contain only carbon-carbon and carbon-hydrogen single bonds. They contain no other functional groups. Technically, that is kind of a functional group, alkane, but we usually don't think of it as a functional group because that's like your main base chain that everything else gets added to. Okay? You can kind of think of like the foundation you build. They all kind of look alike. That's it. Okay? The most basic alkanes, meaning normal alkanes, are straight chain alkanes or linear alkanes. So they're just a straight chain that you add stuff on, or sometimes don't have anything on. The rules for naming straight chain alkanes: all straight chain alkanes have a suffix ane. That's why it's called alkane. Al clearly means I don't care about the number right now, some number. Okay? Ane is the straight chain with nothing else. That's what that one's telling you. All single bonds. Numerical identifiers then used. These are things like meth, eth, prop, and but. It's going to be used to specify the number of carbon atoms in the chain. I wish they hadn't changed the numbering for the months. It would have made our life so much easier. But there's how many of me? 1, methane, right? Also, the drug meth is based on a methyl group and its position in the structure. Ethane You ever seen et al? That's this like it's two or more. So it means two or more, and so et two, ethane. Yeah, et tu Brutus, you too Brutus. Propane, a pro. So if you're looking at baseball, does anybody know what a pro's batting average should be? 0.3. 30% of the time they hit the ball. Only place you can get paid millions of dollars for only being able to do your job 30% of the time. Baseball. But how many cheeks do you have? 2 on your face, 2 on the bottom, right? Butane. Butane. Pent, the Pentagon. Everybody knows the Pentagon, right? Okay. And so, pentane. I know. It's effective, though. You're going to remember it, aren't you? Yeah. Okay. And nobody needs anything else for Pentagon, right? Pentane. Because we have a building that's very famous in the United States. Yeah. Hexane. Hex wrench. 6 sides. Hexane. Okay. Heptane. 7. Yep, you got it. And then octane. 8, like an octopus. Yep, you got it. Perfect. Or the octagon, I guess, but no, it's so much less. Nonane. November. Yep, November should have been the 9th month. Okay. It was. It used to be the 9th month. Then people that weren't Latin messed it up. Added some extra months in there. The October, November, December, right? They should have been the 8th, 9th, and 10th months. December as in decade, right? Nonane, I don't think this actually helps, but this is like the only good example I've ever been able to come up with, is nona, or like nanny, where that, yeah. Nona literally means is a goddess of birth. And so 9 months birth was named after Nona. Yeah. And then you name like Nona your grandmother because they helped you with your birth. And yeah. Anyways, that's where all that root came from. It's a long winding path and it doesn't really help, I don't think. But remember Nona. They did. They just did in Latin because that was the only language everybody could agree on at the time. No. Keep in mind that we'll go in German later on in this course. So science used to be, back before any particular language did a lot of science, it was Latin was like the European standard for science. And then it was English, French, and then English, and then German were the head of science, and everybody did science in those. And then it went back into English. And now there's English and Chinese that are doing a lot of science, right? And so you get English version of Chinese words that are showing up in science now, and English, which is actually probably the best it's ever been. But so anyways, the only one they could kind of agree on is Greek and Latin because they don't change anymore. It helps. Just be glad that you're not having to try to do like Chinese right now, because Chinese had a 6,000 year history in science. Technically, the Chinese actually invented a lot of this stuff before it got reinvented. Yeah. So you should just be happy with it. You'd have to pronounce a Z as she. And you'd be going nuts. All right. So the hydrogen atom of an alkane, this can be replaced by another atom or group of atoms. We call this substitution because you're substituting a hydrogen atom out. Okay? You're replacing that hydrogen atom. And so this is going to be a substituted methane right here. We've taken a methane, we've substituted out with some substituent of some sort, which is why this is G, generic substituent, we don't care. Okay? And this would be like, for example, a substituted butane. Now, keep in mind, there can be multiple substituents in a molecule. The IUPAC name has to account for all of those substituents, and you have to be able to identify exactly where it is. So you're going to notice the IUPAC naming is very similar to like a street address system, okay? Because it kind of is, isn't it? Like you have a main street here, and then you have addresses off of it, right? So it's going to be pretty similar, actually. All right, so the rules for doing it's going to depend on the type of substituent the molecule contains. So the first substituents we're going to introduce is the halogens. Does everybody know what group the halogens is? Yep, the one right before the noble gases, right? And so the ones we typically have to deal with are going to be fluorine, chlorine, bromine, and iodine. Okay? When they are substituents, they're going to be called fluoro, see fluorine to fluoro, right? Chloro, bromo, and iodo. See how they all end with O's? That's to help you out so you can actually pronounce them. Okay? Okay. The nitro substituent, it would be NO2. And so that is the nitro group, like nitroglycerin. Go boom. Okay. Yeah, nitro. Right. Or nitros, also nitro. Okay. And so, well, where do we start numbering when we're counting these things up in our address system? We start numbering with 1, exactly. And we start numbering where there's something interesting. Because it's interesting. We want to know where that is, right? And so, right here we have chloro, because there's a chloro group, right? Chlorine. That's the functional group. We have 1, 2, 3 carbons. And so that is propane. And so you put chloro in front, then propane. There's 2 possible positions that could be. It could be the 1 here. It could be on 2 here. Everybody say okay? And so we put 1 chloropropane. Wait, why did I miss 3? Yeah, just flip it, right? Yeah, we can just flip this around and it would be 1, wouldn't it? So if we put 3, it wouldn't make any sense. It should have been 1 then. Now remember that when you're looking at molecules, they don't actually have directionality, right? They're just spinning around in space. And so there is not actually a right or left direction in molecules. Okay? You're orienting in the way that's most convenient for you. Mm-hmm.
So you put 1 just because it's at the 1 spot?
Yes. Yeah. If it was over here instead, that would still be 1. Because you would start numbering over here. Because that's where the chlorine would be. Okay? If you had another chlorine over here, then it'd be 1 and 3. So you do 1, 3 dichloro. We'll talk about that in a bit. But okay, everybody have our numbering system okay? We always start where the interesting stuff is. Okay? That's where we start our numbering. Now, how do we figure out how many carbons are in a chain? What we have to do is we have to find the longest continuous carbon chain. In this case, we just have single carbon chain right here that has 3 carbons. Okay? Now, notice the words I used. Longest continuous carbon chain. Okay? So longest continuous carbon chain. If we have another carbon that comes off here, that would not be continuous anymore, right? Okay, and so we'd still only have 3. Okay? So be very careful about that. It's something that's going to sucker you in. You're going to be tempted to try to do that, and it's going to cause problems. Okay? So let's say we had another carbon up off of here. Let me draw in. Like that. Yeah. So we still only have 3 carbons in a longest continuous chain. Because we can go 1, 2, 3, or we can go 1, 2, 3. But it's not continuous if we go back, right? Or if we were to do like that. Yeah. So, in fact, in this case, it doesn't matter which way you count. Yeah, you can go 1, 2, 3, or 1, 2, 3. Doesn't matter. Okay. Let's say that we have something like this. That's connected, by the way. Okay. How many carbons do we have? 4, exactly. 1, 2, 3, 4, right? So that would be our longest continuous chain. That's no longer propane. That would be butane, exactly. You got it. And so that would be 1-chlorobutane. We would have to add one more thing to it, which would be this group right here. That's called a methyl. Yeah. And so that would be 3-methyl 1-chlorobutane. That's the methyl right there. 1 carbon. Yeah. We'll go into those rules in just a second. But it's literally just taking your AIN names and putting YL behind it to indicate its branches off. Yeah. Yeah, it's like pretty consistent and easy for the most part. Mm-hmm. We'll go into it in just a second. Let's build up to here for now. Okay, so first step you're always going to do, and this will work for any structure, identify your main chain. Okay, so your main chain or parent chain, depending on which way you want to call it, they both work, is going to again be your longest continuous chain of carbon atoms. The name of the corresponding alkane from the table will be your root of your molecule's name. So that's going to be, you guys know what roots are for English, German, Latin, any of those languages? Okay, this is the exact same concept, right? And so like we could have bend or bending. Those have the same root, right? And this is going to be the same thing. So we have meth. It could be methane, methyl, methene, methine. Okay? But that's the root of your name, is that longest continuous chain. That's going to be called your main chain, your parent chain from now on. It's what everything else builds off of. Okay? You will notice this is actually very similar to Latin or German, if you guys know those languages at all. Okay? Where you kind of just add stuff to your word till it says everything you want to say. All right. So you add the name of your substituent. So your substituent's name should be written as a prefix. This is going to be left of the root. So notice it got added to the left each time of the root, which is prop, right? Okay. If you have a bunch of substituents, you just keep adding them up to the left, and it gets long, 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 long. Okay? Mm-hmm. It does. Yeah, we'll talk about the order in just a bit, but we need to build up to it. So the number of carbon atoms of the chain, this is going to begin with C1 at the end of the chain. That's going to be the first one off of the highest priority substituent. Okay? What you want to do is you want to take these substituents and number them based on what is going to give you the lowest possible numbers for those substituents. These numbers for the substituents are called locator numbers or locants. They're the address off of which that substituent is bonded. Okay? So whatever carbon that substituent is bonded to, that's your locant. Okay? Or locator number. All right. So again, you're going to get the lowest possible number for your substituents. Okay? If there's an argument, we only have one substituent so far, okay? So there can't be any arguments right now. We have halogens, right? It's the only one possible so far. So right now, you're going to give that the lowest possible number for your substituents. Okay? Add the locator number in front of that substituent. So the locator number is going to go to the left of the substituent name. Anytime you have numbers and letters that have to be joined together, you're going to use a hyphen dash. Okay. And so this is going to have it where the hyphen is then going to separate that locator number from your first letter of your substituent name. No spaces should ever appear in an IUPAC name. This is actually kind of an interesting thing because number one, it keeps it all together in publications, so they don't get split up among different lines as much. And number two, it actually is important for file names. I don't know if you guys know this, but old computers couldn't read spaces. So, or commas for that matter. So this right here is just discussing what we had discussed before. Notice that the rules are being followed here. Everybody see that okay? So we went and located our substituent. We then counted our chain. There was 1, 2, 3 carbons. That's our parent chain right there, right? Okay, and that's prop. And then ane, because it's all one single bonds. There's no double or triple bonds or anything like that. And then we have a chloro group right there. It's on position 1. That's its locant. Okay. Notice the dash separating the number to the letter. Okay. Okay, so let's go ahead and look at this one real quick. So here we have how many carbons are our longest continuous chain? Just one. Yeah. So that's going to be methane, isn't it? All right. And that one has a bromo attached to it. Is there any other positions to attach that? No. So you don't need a number there. You can just not put any number. Okay. That actually same thing will happen on ethane as well, which is what we're seeing here. So there we have 2 carbons in our longest continuous chain, ethane, right? It has an iodine attached, so that's iodo. We don't need a number because if it's on either of these, it's the same thing. Okay. Anybody have any questions about those so far? Mm-hmm.
Would it be kind of wrong if you put the number?
Yeah. It'll be wrong in the term of like you doing bad English. Does that make sense?
Yeah.
Yeah. Like using an A instead of an N.
Yeah.
Like, is anybody actually going to not know what you're saying? No. Then you're fine. But will somebody make fun of you maybe? Maybe. Yeah. So, what is the IUPAC name of the molecule? I'm gonna be honest, like IUPAC naming, people mess it up all the time and do minor like mistakes and stuff. So yeah. Like an editor might on a publication go, you need to rename this, but yeah. By the way, that comment I said from my advisor when I was in graduate school, he sent that to an editor of another journal. So he was like a head editor for a journal, and was editor for like 3 journals at one time. And an editor refused to take our publication until we renamed it using the IUPAC name for the compound. And he actually called the guy up and was like, I was here before them, and actually sent that as a comment to the editor that I was here before those fuckers. You can shove this. Huh? So there's other namings, for example, common namings that were around before the IUPAC name. Yeah, kind of like water. Yeah, or like chloromethane. That's the IUPAC name. Dichloromethane, which is my God, I've been sick for like 2 days and now my brain is fogged. Jesus, what the hell is dichloromethane in common name now? I haven't used it in so long, so we can't. By the way, we had to get rid of that because you can't have that in labs anymore without a 50,000. Methylene chloride. Thank you. Yes, CH2 is methylenes, and then chloride for you have the chlorides. It does, and that's why I kind of like my relationship with this is complicated. By the way, you guys can't actually use that anymore. We can't store that anymore. It was the 3rd most popular solvent under the Biden administration. They have now made it so you have to have a $50,000 compliance machine, which is a spectrometer that monitors your air in your lab, if you're going to use it, based on data from a study that had been debunked 5 years beforehand. So the third most popular solvent in industry, you guys can no longer use.
Yeah, they just want to see that.
Oh. Okay, so how do you name it? Okay, so how do we start? Yep, longest chain, which is this right here, right? Okay. Which direction do you start numbering from?
The side that it's closest to.
Yeah, the lowest number possible for this one, right? So, like, if you numbered it the other way, you'd have a higher number for that, right? So, okay, very good. That's one of the places where people have troubles at the beginning, okay? So don't feel bad if that happened. Just remember, doesn't matter right or left, doesn't matter top, bottom. All that matters is lowest possible locand. Okay, and so you got the nitro, perfect. By the way, I don't say if things are right or wrong until we work it up to. And so we have pentane 5, right? The number is going to be 2. Notice how I assemble all these pieces first, and then I write my name out, right? Okay, I highly recommend you do something similar. How I used to do it is I would just write out my notes on the side and then put them all together for the name. Okay? For things like this, you're going to be able to just do them off the top of your head after a while. But we will get things that are like 20 pieces. And you're going to mess up if you just do it off the top of your head. Okay? You try to assemble it all at once. So it sometimes helps to do it in pieces. Okay, so the 2-nitro pentane, perfect, exactly right, excellent. Does anybody have any questions? Get lost? No. Okay. So remember, right now we're relatively simple names with not a lot of steps in them, but just get this process down really well. And then notice it's an incremental process, right? You can do it small piece by small piece by small piece. This is very important for science. It's how you handle big situations, right? You break them into small, tiny pieces that are manageable. Okay? So get used to doing this process just small piece by small piece. You don't have to worry about the 20 character names, okay? You just have to worry about each piece, right? Okay. Okay, so this right here is some different examples that we can kind of explore these numberings a bit. So this one's the correct one right here. Notice that this right here is 1, 2, 3. That gives us the lowest possible numbers for both of these, doesn't it? Okay. The other way would give us a higher number for both. Okay. But what if we have something like this, for example? Which one's going to be correct here? Well, you already know because I put correct, but the lowest possible number for our substituents would be these two being 1, right? And then that being 2. If you put a 1 over here, on the other hand, you're going to get 2, 2, aren't you? Yeah. And so that would end up with these number 2. Okay. So let's talk about adding prefixes. We're starting to get multiple prefixes. My goodness, things are progressing. Okay. So write the name of each substituent as a prefix. So if you have multiple different substituents, each one is going to be written in as a prefix. You're going to order these substituents alphabetically, which is how you order them. And so literally just by alphabetical order, okay? By the substituent name, right? The reason I'm stressing that is the next thing we're going to do. Mm-hmm.
Is that including this prefix?
Yeah.
Substituent's name including
The prefix is the substituent's name. Yeah. So like iodo, chloro. Chloro would come before iodo. Yeah. Fluoro comes after chloro before iodo. Okay. Okay. The thing you don't want to add on, and why I stress this, is this part here. So if you have more than one of the same substituent, you don't write it out over and over and over. Okay? You don't write out iodo, 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 iodo. Because you could have 20, 30. Think of like a DNA. A DNA could have the same substituent literally tens of thousands of times, right? You imagine writing those all out. Oh my goodness. So what we do is if you have multiple of the same substituent, you're going to use these multiplying prefixes. These are not going to account for the order, though. Okay? You're not going to include them for alphabetic order. You're going to ignore these. So di is 2, tri is 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona, deca. I think everybody knows those from Gen Chem and has those pretty well down. But if you don't, those are that right there. By the way, di and bi actually both are interchangeable, but you should use di. It's just better English here. It's technically not English, but you get the idea. Now, again, that's how many of them you have. So let's, for say example, I have 3 chloros on a structure. What do I put? Trichloro, right? If I had 4, tetrachloro. Okay. Doesn't matter if they're right next to each other. It's just that's how many chloros I have on that structure. Okay. So you're going to add 1 locator number for each substituent. You're going to use a hyphen to separate any number from any letter. You'll use commas to separate the numbers. We're going to practice. Yeah, this is a very, very practice-oriented science, just like any language class would be, right? Because realistically speaking, this is a third of a language class. And then conceptually is another third. And then realistically, it's like a third art class. Making different structures and using reactions to make stuff. So it's the science where we got a little bit jealous of the other subject matters. And we just took them all. Okay. So go ahead and start coming up with the name. Work as best you can through it. Again, just like we would do in like a Spanish class, this is my, you all break apart and start talking to each other. Use that language. Communicate. So please do make sure you're working through it yourself as well. You'll never know where you have your issues if you don't. Okay. It's not like I'm like punishing you if you get this wrong. So this one's your freebie to get wrong and learn from that mistake, right? Even the homework, I'm going to penalize you 3%. I'm terrible. In case y'all wonder, the homework's 3% penalty is literally so you don't sit there guessing 30 times. Like I've had people do. If you've guessed 10 times, it's just not worth guessing anymore. Come in and talk to me, okay? Okay, folks, I'm going to go ahead and move forward. Hopefully you got some far enough that you know your weaknesses and issues. Yes. Mm-hmm. Yep, you need to include the locats or locator numbers. Okay, so the first part, longest continuous chain, right? So we just count along our number of carbons, and that's 6, isn't it? Okay. Which way should we count? This way or that way? Yeah, right here is going to give us our lowest possible locants, isn't it? Okay, and so we count off 6, and now we have to figure, well, what substituents do we have and what's our root name? Okay, so parent root name is hexane. Yep, 6. We only have single bonds, hexane. I know I keep saying that like it's a thing, but it's a thing later. We'll get to it. Okay. Now we have to come up with our substituents. What's the names for those substituents? Fluoro and nitro. Very good. Very good. So fluoro and nitro. Which is alphabetically in front of which? Fluoro. Very good. How many of each? 4 and 2. Perfect. Okay. 2 is what? Di. So what's the nitro going to look like? Dinitro. You got it. And how about 4? Tetra. Very good. And so it's going to be what fluoro? Tetrafluoro. Very good. Okay. Then we have to do our locant numbers. And so this one here is 1, 2, 3, 4, right? And this one here is going to be 1. 1 again. You got it because there's 2 of those, isn't it? 3. Perfect. Yeah, you got it. Yeah, you got it. Yeah. Okay, so all together, it's going to be, once you assemble it, 1, 1, 3, 5 dash tetrafluoro dash. You don't want to pronounce the dashes, by the way. You want me to say it without the dashes? Okay. 1, 1, 3, 5 tetrafluoro 1, 4 dinitro hexane. Everybody want to try it with me? Come on. Everybody with me. 1, 1, 3, 5 tetrafluoro 1, 4 dinitro hexane. You don't have to rush through, by the way. You can add a little pause there.
How'd you get 4 on
The fluoro?
Yeah.
1, 2, 3, 4.
Or no, I'm saying like for NO2 on the top, right?
First carbon, second carbon, third carbon, fourth carbon.
Oh.
Yep. No problem. By the way, if you have a very long structure and you know how many carbons there are total, you can also count from the other end. And so I know there's 6. I can go 6, 5, 4. Like here, it's not going to make a difference. But if you ever get a long, more complicated structures, it can actually make it easier. Okay. How about if there's a locant number tie? So now we got tie. Uh-oh. Alphabetically, yeah.
So the first one is the least.
Yep. So bromo comes first alphabetically, and so it gets the lower number. Yep. Fluoro is going to get the higher number because it's later alphabetically. Literally, I put the lowest number first. That's fine. You're okay. Okay. So naming straight chain alkyl groups. These are what I was referring to before. Notice the alkyl. So some number, ill. Okay. So this is going to be substituents that are straight chained alkanes. So they're substituent alkanes. They're branches off of your parent chain. Okay. Think of them as little branches off your trunk. Just like a branch is not called a tree. These are the alkyl groups. Everybody knows plants a little bit. Okay. You got a trunk, you got a branch, then you got a stem, right? These are the branches. You have the root. Now we have the branches coming off. It's like a tree, right? I know. Chemists are literary too. All right. So naming straight chain alkyl groups. These are going to be identify the corresponding alkane that would correspond to, i.e. if it has 1 carbon, it's methyl, right? Because it's methane. You're going to change the ane portion, A-N-E, to YL. That's referred to as the suffix, just like your names have suffixes. Okay. And so again, we're going to take the root. We will change out that root to ill so that we can use as a prefix substituent. Okay. So this is methyl right here. This little wiggly chain here is our root. Okay, that's our parent chain. And so it's coming off. It has 1 carbon, methyl. This can be abbreviated as ME, by the way. Most of these groups have abbreviations, the smaller ones, so that you can easily write them in on structures. This is ethyl, 2 carbons, abbreviated et. Propyl, 3 carbon chain, abbreviated pro, PR. And then we don't usually abbreviate these longer ones past butyl. So butyl is 4, Bu, pentyl, hexyl. If you had 10 of them, it'd be decyl, right? You just keep going. Okay. Let's try it out though. So right here, we have a carbon chain. See, that's our longest carbon chain right there. That's continuous. Okay, and that's 6 long, right? And so we have hexane. Off of that carbon chain on the 3rd position, there is a 1 carbon chain, right? And so that's methyl, because it's 1 carbon. Anybody getting confused or lost or? Okay. Yeah. Yep. Longest continuous chain right here, right? Be very careful. Some of you are going to be tempted to try to include this in your longest continuous chain. And it just is not a continuous chain, right? Yeah. Very common mistake. Okay. So that's 3-methylhexane, of course. All right, so here we have another example. This one right here is going to be longest continuous chain is 8 carbons. If we were to count here, 1, 2, 3, 4, 5, 6, 7, 8, we'd have the same number. Everybody said okay? Okay. Does it actually matter which one you call your longest continuous chain? No, it doesn't matter. You could have done either way. Just easier if you do a straight chain. Okay, and so this one here has 1, 2, 3 carbons in that, right? So that's going to be called a propyl. 3 carbons, pro, right? So that goes to propyl. So I have an octane. That's my parent. I have a branch, which is a propyl. And then I have 2 chloro groups I have to deal with, right? Okay, so my parts right now is a dichloro, a propyl, and my parent main chain octane, right? Okay, so I look at this. Chloro versus propyl. Which one comes first? Chloro, C, right? And so my first one is going to be 4,4, because these are off the 4th carbon here. Dichloro. Then I'm going to have a 5, because it's the 5th position here. And that's propyl. And then that's octane. There we go. You see how you just work through the pieces and you'll get it? Okay. You don't have to know the whole thing at once. Just get the pieces, then assemble the pieces. Okay, now be careful when you're numbering. There's some things that can trip you up. So the way in which the molecule is drawn can really influence your perception and really cause you to make mistakes, okay? Remember that these molecules don't exist in reality as perfect little lines on paper, okay? And you don't have to write them as perfect little lines on paper, right? You may have noticed that when you're using the tool on the website. Everybody's probably made some structures you go, what the heck did I just write? And you have to look at it again, right? So this right here is one example where you can really mess yourself up. See that this looks like it's the straight chain, right? But is that the longest continuous chain you can make? No, you missed one, didn't you? Yeah. You missed one down here because it looked like it was not in that little chain thing, right? But it was. It was part of the longest continuous chain. Okay. Just like a normal chain, it doesn't have to be stretched out perfectly on the ground, does it? Okay. It can be wiggly and waggly and all over the place. Little curves in it, whatever. Now, here's another example. Down here, we have the methyl right there, right? Versus an ethyl up here. And so people have a tendency to look left to right and not look at the ones above and below. And so that person started counting here and never recounted. And if you would have recounted, you would have realized you have a longer number here, don't you? And so this actually starts up here. Okay. All right, so let's talk about some branched alkyl substituents. Oh my goodness. Just like trees, those branches are not all together and stable, by themselves. You can have other branches coming off of branches. Ah, dang it. Shoot. Naming branch groups. So identify the main chain of your branch group. You literally just reuse the same rules just on the branch again. Okay? So we're going to look at our branch. We'll identify our main chain of our main branch. Okay? We're going to assign the alkyl group's root name as that main branch. Then we're going to take the number of carbon atoms of the branched alkyl group's main chain. The atom at the alkyl group's point of attachment will always be carbon 1. So right here, that's always carbon 1. Because our parent is here, that's the attachment to the parent. Kind of like if I point out to that tree over there, where's the attachment point for that branch? It's to the trunk, right? The parent, the root. Same thing here. Where's the start to that? 1 always goes at the parent. Okay? So whatever's attached to the parent, that's always number 1. It actually makes your life a little easier, by the way, because where's number 1? It's always at the parent. Okay, so you're going to then add prefixes and locator numbers for those things that branch off. Don't worry, we're going to actually do it. Okay, so right here is a fairly easy example. So if we look here, what we see is we have a 2-carbon chain here, right? So 1 there, 2 there. Where's our locant number get located? Number 1 is always the thing attached to this parent here. That's a little squiggly line, okay? And so number 1 is there, number 2 is there. We have our numbering done. The next thing we're going to do is the substituents. Well, we have a 1-carbon substituent, don't we? And so that's going to be a methyl. It's on the number 1 location. And so we go 1-methyl, then it's ethyl for 2 carbons, and that's going to be the substituent. Whatever parent we had added that to, we just add that whole thing in. Okay? If these get complicated enough that they're going to start causing you problems in your naming, you just put parentheses around the whole thing. Okay? Those are called complex substituents. So if this gets complicated enough, it's going to cause problems in your naming. You just are going to put parentheses around this whole thing. Okay, so let's go ahead and try naming this substituent right here. So the first thing we need to do is we need to figure out what was going to be our parent for this. Okay, and so our main chain here is 1, 2, 3, 4. That's going to be a butyl, right? You start at the parent. Right here. Remember, there's a chain here. So this is the main branch. Over here, see the squiggly line? There's a longer chain over here. So we're just discussing this part, which is this branch part, but we're only looking at a branch. Huh? We are. Yes, this is just a substituent right here. We aren't naming the parent right now.
So if we name the parent, that would all be added to the parent.
Yeah. So over here, where there's the group, that would be a parent name. And you can tell easily because this ends with "ing." See how it doesn't have the ing? So we don't have the root, the parent. We don't have the main structure yet. We're just learning these right here, which are the branches. Okay? Okay. So let's get this branch named, and then I'm going to give you ones with the actual parent in it. And you'll see they're longer chains. So we'll have a longer chain available. So right here, we are again going to have butyl. And this is going to have 2 methyl groups. And so that is dimethyl. They're on position 2. Why am I not starting with 1 over here? Yeah, you got to start at the parent, right? Yeah. You got to start at your root, your trunk, if you will. Okay, which is right here. Okay, so, and again, this one here, 2 carbons, so that's ethyl. Ethyl becomes before methyl. E comes before M. That's the position for the dimethyl. Okay. And so this one here, the ethyl, is on the first position, locator number, 1 ethyl. And then we have 2 of these dimethyls, so 2,2, dimethyl. And then this one right here is that main branch. And so that one's going to be your butyl. Okay, now let's go ahead and do this for a full name. Everything's included. We have our root, everything. Okay? Right here. We have 6 carbons in this one. That's hexane. And that's going to be our parent right there. Okay? That's our main chain. Okay, now we need to get the substituents off of that. And so we have a nitro right there. Right here, we have a methyl ethyl group. See, there's 1, 2 carbons here. So that'd be ethyl, right? And there's a methyl off of it. So that's going to be a methyl ethyl. Okay. So all together, this is going to be, this is on the 3rd position, so 3. Notice the parentheses to keep that all together in one place, right? So that we know, hey, that is one substituent. These aren't split off into different groups on this. Okay? And so that's going to keep that all together as one substituent. And that is 1 methyl, because the first position here, right? Ethyl for the 2 carbons here. And then that's going to be the 2nd position for the nitro, hexane. Okay. Again, I never, ever, ever try to get the entire name all at once like that. Notice even when I'm talking about it to you, I'm breaking into pieces, right? Because you break it into pieces. You don't do the whole thing at once.
So for the 1 methyl ethyl group, do you need the 1 since you said before that it's kind of implied?
You do.
You do.
That's because this, technically, actually, you are right. You don't. Because if you had put the methyl here, that'd be propyl, right?
Yeah.
But by convention, they do put it here.
Okay.
Just because they need the extra clarification usually.
That's for the branches.
Yeah.
Okay.
But no, you're right. If you didn't put it, people would still be able to know. Yeah. So. Okay. So once you have that root right here, okay? So this is this hexane, right? So that's your root. From there, that's like the main trunk of a tree, right? So now we're describing the branch here, okay? And we're going to start with this carbon here because that's the first one on the branch, okay? So that'll be carbon 1 on that branch, okay? So there are 2 carbons as our longest continuous chain on that branch. Can you see that part? Right there. That's carbon 1. That's carbon 2. Exactly. Coming down this way, right? Okay. So that's the ethyl. And then off of this ethyl here, there's a 1 carbon 1. That's a methyl. That doing better? Okay. So like if we were to, I'm going to use a squiggly line for the hexane part. Okay. That's the hexane, right? And then we come down, that's carbon 1, right? And then the next one, carbon 2. And that would be the ethyl. And if we just had that, that'd be ethyl, right? No. But we have another one, don't we? And it's off of this ethyl. And so what we have to do is that is 1 carbon, and so that would be methyl. Okay. Huh? Why would it be ethyl methyl? Because the longest continuous chain. Yeah. So basically, you always think of it as we have a relative coordinate system. That's what we're using here. And kind of like if you branch off of streets, right? You have like North Main, and then you have a street coming off North Main, right? And so, like the street coming off of North Main, it gets a whole new numbering system, right? 1, 2, 3, for its houses. Or like the rooms in this building, we have 301, but we also have 201, right? That's because we're branching off. We're doing the same thing here. We're just using that same coordinate system every time to keep it consistent and easy. And so longest continuous chain, and then the branch off of that. By convention, you should put the 1. Okay, especially in any sort of complex substituents like this. But technically, in this one, you can ignore the 1, and you still have the same structure. So you could probably get away with that if you were ever writing this out for something. But the correct way would be to put the 1 whenever you have complex substituents. And kind of think of it this way. You're not really saving much writing if you drop those numbers at this point. So the extra clarity is probably worth more than trying to say one number, right? Yeah. Whereas the other ones where you have simple structures, it's a significant part of the name, right? Okay, let's go ahead and try this other one over here. So again, we look at the main chain, we try to find that parent chain, and that's going to be this 10 long one, okay? Now, note that if you were to start counting over here and it would make a longer chain, that one would be the main chain, okay? It would be the parent, all right? 1, 2, 3, 4, 5. But in this case, we actually have equal lengths of chain. So what would happen is we would take this chain as the main chain, the parent chain, because of the substituents. Okay? It would be more complex naming that substituent with this stuff than it would be to do this one. Also, our functional groups that are more interesting are on that side. So those have higher priority. We haven't really encountered things with significantly higher priority yet. That will come in once we have those groups.
Where's the other?
For this one here, right here. That's why it's the 1.
I was gonna say, but it looks like that could be a methyl group with another methyl coming off of it and 2 ethyls.
But there's not any branching. So like here's your chain for the branch, right? Okay. So let's go ahead and look at this. Okay, we got the 10 carbons, we have 3 bromos. Everybody's good with that, right? Tribromo. Okay. Okay, so right here is where we have our start of our branch, right? Okay. Okay. And that's position 1. So the first thing we need to do is find the longest possible chain off of there, right? And so over here would be 1, 2, 3. Over here would be 1, 2, 3, 4. And so this one's our longest possible chain there. And that's a butyl. Okay. 2 methyls right there. Yep, exactly. And then an ethyl there. And so we have an ethyl right here, 2 methyls here. This would be position 1, 2, and we put all that together. Okay. Does anybody need me to put that together, or did I lose anybody there? Okay. It is a practice thing. Again, this is a language. You're never actually going to get it until you practice it. You'll either think you get it from me saying it, or you won't think you get it from me saying it. It won't. Either way, you won't get it because you haven't practiced it yet. Okay. Okay. Note that all goes into a complex substituent right there, and that's summed up. Okay, let's start with cyclic alkanes. So if a molecule contains at least one ring made entirely of carbon atoms, that ring will act as a root of your molecule. Okay, can act as a root of the molecule. And that's called a cycloalkane. Cyclo meaning it's in a ring structure, right? Kind of like cyclobike, right? Or cyclone. So this right here would be cyclopropanes. Yeah, it comes back together into a ring. Cyclobutane, cyclopentane, cyclohexane, and so on. Okay. This right here would be them as a substituent. So if they end up as a substituent because they're not the longest continuous chain, what you're going to see is they'll be called cycloalkyl groups. So for example, cyclopropyl, cyclobutyl, cyclopentyl, etc. Now, how do you distinguish ring carbons from chain carbons? So that a carbon as part of a ring is not going to be counted as part of a chain. They just don't mix. And that's because rings have no end or beginning points. They're enclosed, right? So you don't mix them in with the chains when you're counting. Okay? So you're going to compare the number of carbon atoms in the carbon ring to the number of the longest continuous carbon chain. If the ring has as many or more carbons, the longest continuous carbon chain, your ring is going to be your root. Okay? If your chain is longer, then it's the root. So equal, you go with the ring. Okay? If the ring is longer, go with the ring. If the chain is longer, go with the chain. Okay, this is an example right here. So again, our longest continuous chain is 8 carbons. Notice we do not count the carbons in here. We don't like go 1, 2, 3, 4, 5, 6. Okay? Right here, this is our longest continuous chain. That's in that ring right there. Okay? Okay, because again, even if they were equal, we would take the ring. Okay? That will be the end of that part, and we will start here next time. You all have a great day.
So you said even if they're equal,
Yep. Basically, the rule is for chemistry, if it's more interesting, that's the one. If it has more interesting chemistry.
Yeah.